anybody here from Houston and going to catch me if I tell lies about Houston? Okay, because I may have to fudge a few things as we go along. What we're going to look at today is the Deer Park fire. So in March of this year, a bunch of petrochemical storage tanks in the Deer Park area of Houston caught on fire and spread this big, toxic cloud over the city of Houston. At the time, the people on the ground were told that they didn't really need to worry about the air pollution because this cloud would pass, high overhead and fall on the desert somewhere. But at one point during the crisis, a benzene tank leaked, and benzene came out into the air, and they had everyone shelter in place for a day. So that's the issue that we're going to be looking at. So let's start by looking at the area in GIS, get familiar with the location, and also just get familiar with the software. This piece of software is called ArcGIS Pro. Has anybody here worked in a GIS yet before? And of those people, how many of you used an Esri product? Okay, anyone use QGIS? And I'm sure you used ArcMap because Arc Pro is pretty new. All right, this is ArcGIS Pro. This is the newest software. It's the future. This is where Esri is committing all of its future efforts. It's a combination of the programs that used to be called ArcMap, ArcScene, ArcGlobe, and ArcCatalog. They've rolled them all into one. And it's a beautiful software. It's brand new, and it has considerable additional capabilities over what ArcMap was able to do. So here we see a base map, the imagery base map, and an outline of Houston, Texas, and the location of the fire. So you can see that the fire is there sort of on the port side of the city. If you were looking at this, which way would you guess, without looking it up, which way would you guess that the wind blows? Out towards sea?
Well, I think it goes eastward, because when I fly to the other side of the country, it takes me longer. But when I come back, it's shorter, but I don't know.
My rationale was that the wind comes in from the sea. So I was thinking there would be a westward wind. It turns out we're both wrong, but but that was my initial impression. So here's one thing that's kind of fun. You can zoom in here and really see the detail of what's going on the ground. You can see the tanks, you can see the industrial area, and if you had work that needed this kind of detail, you can actually draw these. You can digitize right in the GIS over any kind of features that you see on the landscape. So I just put a point location to show where the fire was. Zoom back out to see the area.
Yeah, for that, I gave an example of incinerators. You could actually find the smokestack.
Exactly.
Because if you just had the address of the facility, it might just put it at the center of their whole campus, but you might want to know exactly where the smokestack is.
So that's actually the first lie I told. I have the wrong set of tanks, but it's quite close to the real location. So, but we call that a point source of pollution. You have a point origin that the pollution's coming from, and so I mapped that. The things I want to look at are the locations of vulnerable population and the likely spread of the pollution. So I imagined that we wanted to do some sort of intervention. We wanted to find where to send extra federal money or mobile health vans or maybe evacuate people or go door to door and say, you may have been exposed. And I did, a very brief amount of research and found that the people who are most at risk from these kind of pollutants are pregnant women and elderly people. So I just wanted to get a sense of the population. Where are the elderly people in town? Where are the pregnant women in town? To begin with the elderly people, I looked at the U.S. Census. Now, have you folks all done work with census data before? A couple? And when you did that census work, I'm assuming it was tables, like you did statistical analysis on tables, you didn't actually map the information. Okay, when you go to the census website, and some of you may have done this and some of you may have not, but when you go to the census website, you probably have landed at American Fact Finder, which allows you to specify a geographic unit like census tract, block group, county, and then to find certain variables about that geographic unit and download a table. The table looks like this. Here's a very truncated example. And the important thing to know is that the table you download has no geographic information. At this point, when you download the table, there's numbers, there's statistics, but there is no like how to put it on the map. You really do need GIS to do this. So the other component that you would need to map census data is there's a companion site that allows you to get what are called tiger line files that are the actual geographic boundaries of whatever census unit you're interested in. You download the geographic unit and the table, and they have a matching field, and you can join these together so that each geographic unit is associated with its numbers from the census. Now, like I said, this table comes like this. It has far, far more information than you probably want. And it also, and again, I don't know how much computer work you've done, but it has 2 header rows. And the first header row is friendly to GIS. It has short labels and no odd punctuation. The second row is human readable. We like that. We like to see total estimate margin of error, but GIS can't handle that row with the semicolons and the long names. So you do have to do always have to do some cleaning to get this table ready to bring into GIS. Okay. But I certainly won't bore you with how to do that. So here we have the census tracts, the outlines of them. And one thing that's kind of nice about GIS is you can click on one and get its associated information. There is a table hiding behind this. For example, I can open the attribute table, and it looks a lot like an Excel table, and it behaves a lot like an Excel table, but it's now internal to the GIS. And you'll see that I cut down those fields tremendously. I gave them nicknames like total pop and 75 plus to indicate like the number of people that were 75 or older. And I've actually added a whole bunch of other things. But I've managed to join the statistic to the spatial unit. What can I do with that? Well, for one thing, I can look at it. I can change the colors, what's called the symbology, to just visualize where all the elderly people in Houston are. Okay? By unit, by census tract unit. There's a common mistake that a lot of people make when they're doing census analysis. They only look at the raw number of people living in some unit. Sometimes, for some purposes, it's appropriate to divide the number of people with some characteristic by the total population in that district, and you can get what's called a normalized map, where you're looking now at the density of old people relative to the population. So here, there's a risk that what you're seeing is just where the dark colors might just be where a lot of people live. It happens to be where a lot of elderly people live, but it's also where a lot of people live. So by normalizing, you can kind of subtract that effect out and see where the greatest density of elderly people per population is. That's a familiar concept to everyone? Okay. But now think, if I were going to design some sort of intervention do I want to reach the census tracts with the most elderly people? Or do I want to reach the census tracts with the greatest density of elderly people? Which do you think would be more useful for this application? Nobody? All right, it is my opinion, my unprofessional opinion, that we should try to reach the most raw number of people. That if we were going to put money into something or send some sort of help, we would want to reach the tracts that had the largest raw number of elderly population.
I guess if you had limited resources, say you could only send out a certain number of informational flyers,
yes,
then maybe, say you had to send it to the whole tract to cover, so you didn't know exactly where the elderly
right.
people live.
If you had to get it, yeah. But in this case, where I'm assuming we're either just sending dollars, or we're sending some sort of targeted intervention, like I said, like a mobile health van or something, you might actually want to locate it in the places where the largest number of elderly people live. That was my thinking. So I decided to go with the raw number instead of the normalized number, but I wanted to make you aware that this is like a common question that people have to ask themselves in GIS all the time. Does anybody know, by the way, what this kind of map is called when you're looking at one kind of geographic unit, but you're seeing a different value on it? Do you know that?
I don't have an answer to that question,
Uh-huh.
but I have a question given your previous statement.
Okay.
So if the point is some downstream public health intervention, do you think the outcome of that intervention would be changed based on whether you normalize or not?
Well, yes, because
Could you somehow measure that effect when you try to weight your decision to?
let me show you how I create the formula that weights that decision. And after you see it, we can ask again and we can think about it, okay? Because yes, you absolutely can put weights in there. But I'm thinking normalizing is basically a type of weight. You might just weight and unweight. So let's look at the things that go into the decision and then we can decide, okay? So back to what this kind of map is called, where these blue colors don't really exist in the world. It's a visualization. We're seeing a value shown on these census units. That's called a Choropleth map. Is that something that maybe you heard of maybe back in high school geography or something? A Choropleth map? So this is a Choropleth map. All right, so that's the elderly people. We have some approximate understanding of where the elderly people live. Let's consider where the pregnant women live. Okay. So I got a bunch of addresses, and I know you all talked about geocoding already on Wednesday. Geocoding is the process where you have a table with addresses, and the GIS will find the locations of those on the map for you. Geocoding doesn't always go well. This is yet another little fudge I'm showing you. Behind this geocoded layer, let me zoom to the whole layer, you will see that we had a few failures. We geocoded an address out here in Alaska and a couple in the Midwest. If I were doing this for real, if this was a real study that I was worried about, I certainly would have either removed or corrected those. Okay. So here I have all the geocoded addresses. It's actually kind of fun. I put the street base map on so that you can zoom all the way down. And if you click on the point, it gives you, oh, that one doesn't, I have to turn this one off to get the address. Hold on. If you click on the point, you should be able to get the address. So this should be Vinemont Lane. And if you zoom in enough, you can usually see the name of the street. And it's just kind of fun to verify that it really does show up where it's supposed to. Of course, the base map is not resolving here. I actually might not be on Wi-Fi. Usually you can zoom in and see the locations. All right, so here are the pregnant women in Houston, Texas. This is a classic public health situation. You have some data that's on census tracts, and you have other data that's on point locations, and you have to decide, how am I going to get these to be compatible so that I can analyze them together? Does anybody know any considerations that you might take in making that decision? Do you think we could run this kind of analysis on points at this point? We have census tract locations of elderly people. We have point locations of pregnant women. Could we run this on the points? No. Do you know why not?
Because it doesn't have like corresponding census tract information. Like, don't you have to have like the same schematic, like spatially, to like compare two things?
Kind of, yeah. We want a common support. If we tried to somehow break apart those census tracts to get them to match this finer unit, we would be telling a lie. We would be committing what's called the ecological fallacy. You can never move, I don't want to say never, without sophisticated mathematics and auxiliary information, you can never move from a coarser unit to a finer one, okay? Therefore, your strategy is usually to move from the finer unit to the coarser one. We would like to aggregate the number of pregnant women per census tract to the census tract level, and then do all our analysis on those census tracts. Now, I know on Wednesday you guys talked about a sort of catch in that process as well. You all talked about the modifiable area unit problem? A little bit? Okay.
We'd love to hear your perspective.
Basically, what happens with the modifiable area unit problem is if you are working in some context that requires correlation, the coarser units you use, the stronger the correlation looks. Now, we're not going to be doing anything today with correlation, so we're pretty safe to aggregate these up to the census tract level, but I just, because I know you've talked about it, this is something you should be aware of. If you have a choice between census block groups, census tracts, counties, and states, chances are your results are going to look artificially good if you work on the largest unit. Okay, so, but I think we're pretty safe for our purposes here to aggregate to census tracts. There is a tool called Spatial Join that will take the census tracts and count the number of points that falls in each one. So I ran that. I won't take the time to run it for you. But here are the census tracts, colored by the number of pregnant women in each.
Can I ask you to give your thoughts too? So you could technically take each census tract and get the midpoint, right? And just use that as a point. So what's the issue with that?
Those points wouldn't line up with these points, though. I mean, just locationally.
Because it's in a group.
Yeah.
Versus.
I mean, just because you're
Just
representing the area as a point doesn't mean it really is a point. First of all, like there is no point location that has 35 elderly people at. I mean, maybe an apartment tower or something, but here I feel like we're safest to go with the aerial units. By the way, we're catching me in all the lies I told to get this demo ready. But do you think anyone actually gave me the addresses of the pregnant women in Houston around March 20th? That's pretty sensitive information. And I just kind of did this entire project with Google. So just between you and me, these are gas station locations. But just for practice, we're going to treat them as pregnant women. Okay. All right.
In a real study, though, you would.
In a real study, you might be able to get that access.
Their
Yeah.
homes.
Yeah.
Couldn't you say you were lacking data, you thought about where certain populations tend to spend most of their time, you could kind of use markers like gas stations or something to extrapolate a little bit.
Well, you certainly know where the population is, right? You know where the total population, even if you had an indicator like on average in Texas, there's 4 pregnant women per 1,000 people, you know, you'd be able to kind of make a guess. Yeah, absolutely. Okay. So next, let's stop talking about people and their vulnerability. Let's start talking about the good stuff, which is pollution flying through the air. Okay. It's called dispersion. So give me some thoughts to how we could show who's going to be affected by that fire smoke. What kinds of things could we try? There's a very common one that's used a lot, and it's called create a buffer. We could say that, you know, there's some toxic event, and everyone in a certain radius of that event is affected. And in fact, I did not do that because I wanted the chance with you folks here to actually run through one of the tools and show you what it's like to execute a GIS tool. It's pretty simple. So I can go to the analysis toolbar and open my toolbox. And in my toolbox, I happen to know where everything is. And up here in analysis tools, we have a toolbox called proximity and a tool called buffer. The input feature will just be the location of that fire. And what do you think would be a good radius to talk about, like people who might be affected by the fire? 10 kilometers, 20 kilometers, something like that? I will just try one. So we give it a distance, and we give it a unit. And we just run the tool. So, I mean, in a lot of cases, this is just software. It's just picking choices off menus and making the tools run. The difficult part is understanding what tools to use and what you get out of them. So what this buffer gives us is a polygon that shows all the area that is within 20 kilometers of the fire. I reject, this is very common, this is what a lot of folks do, and for some applications it's correct. But in this case, we have a windborne plume. So I just wanted a little something maybe a little closer to how the smoke really travels. I generated a plume, and this is what I'd call advanced GIS. I actually had to write a script to do this. This would not be something that comes out of the box with the program. I made a few assumptions. I said that the fire is putting out 1 unit of pollution per hour. I don't know what that unit is. At the end of the day, we could go find out what the unit is and multiply. I said that the wind is blowing due west, and that each hour that pollution is being distributed out to the west. And then I ran a recursive process that went 100 hours and continued to add pollution where supposedly the wind would take it. Lots of room for inaccuracies there, and lots of things that I could get right if I had the actual science for how this travels. So here's the result. And what it's showing is that as the wind blows to the west, obviously the people due west are getting the most impact. This layer is different from all the layers we've seen before. Can somebody try to get a general description of what's different here from those Choropleth maps that we were looking at previously? What's the unit here? Like what things am I seeing? I'm not seeing census tracts. Let me zoom way in. Maybe I'll be able to tell if I zoom way in. It is a plume. Let's see if I can see somewhere that you get it. Oh, that won't do. How about out here? These are pixels. These are little tiny squares that cover the landscape. They're not any kind of like government units, like a census tract. They're not point locations. This is called a raster, R-A-S-T-E-R, or sometimes it's called a surface. We're seeing a surface of the pollution. We're seeing the amount of pollution deposited at each pixel location in this image. So that's very different. Basically, all of GIS is divided up into two paradigms. Usually you're working with vector data, which is points, lines, or polygons. Or you're working with raster data, which is values in a surface.
What value? Is it like an arbitrary?
Here it's kind of arbitrary because I just used arbitrary numbers. I mean, all it's showing you here is a relative value. Who got more than who?
This is, I guess I'm kind of confused about like what, like is it a concentration, like physically, like what is it? Or is it like a relative distribution of pollution as like a non-defined? Okay.
It could, but if you had.
If I had the right data, yeah, I could get like the actual, micrograms per whatever. But I don't have that, so right now I started with one dump of arbitrary units an hour. I propagated that out across space. So yeah, I have a value, but it's not a meaningful value. Okay. But here's the thing with a raster. Remember how I could click on a census tract or a point and get the information? I could either get the address of the point, or I could get maybe the numbers that go along with the census tract. When I click on a raster, I can get the actual value that is held in each pixel. Now, again, these are kind of arbitrary values, but you can see that it makes a continuous surface. Okay, and
that pixel has 0.052 units of pollution.
Yeah, basically, right. Okay, and if we went, way up here into the yellow, we would get a smaller number. Okay. So it's just important to me that you understand that the two different types of data. They call them models, two different models of data. So let me zoom back out. So now we're talking about unit incompatibility. We had polygons, we had points, and now we have something completely different. We have pixels. So we need a way to move these pixels into a compatible unit, into like a census tract type unit. There's a tool for that. There's a tool called Zonal Statistics that for some sort of polygon zones, like census tracts, it will either pick up the average value of this raster for the census tracts, the maximum, the mean, count, all that stuff. So I ran that. And now we have a compatible base of data. All right. So now we have the census tracts that are the most affected. And each one knows the average value of pollution in that census tract. Okay. So now I've got three ingredients. I've got number, elderly people, number, pregnant people, amount of pollution. I can combine these into some sort of formula, some sort of index that talks about, the risk level, say, in a particular tract. I had to do some math fuzziness because in the case of the population numbers, higher numbers, well, actually here the higher numbers meant you were at risk too, but these numbers are so small, I had to inflate them a little bit so that everything was like on a 1 to 5 scale, for example. So let's look in the attribute table before we go on. Not that. Here. So in the attribute table, I converted the raw numbers to scores so that they would all be of comparable size. I have a pregnancy score. I guess I did it on a 10-point scale. A pregnancy score from 0 to 8, an elderly score from 0 to 8, and a pollution score from 0 to 8. And then just to get a total score, I added them. That was extremely simplistic. I could have done a weighted average, I could have multiplied them, I could have multiplied some and added some. I mean, you can come up with quite complicated metrics, but just for simplicity, I went across the columns and I added them.
Can I ask, when you created your scores, did you just take like 10%?
Quantiles.
Okay. So
I just did quantiles here, yeah.
Okay, make it even. Okay.
Yeah.
You could do something.
You could do a lot. Actually, you're a little bit limited in. You can custom divide up the bands, but default in here you get equal interval quantile, something called natural breaks, which is it puts the breakpoints at like in between clumps. There's only about 5. So if you had something fancier, you would have to custom set them, but you can custom set them.
Yeah, like if it was a trimodal distribution.
Yeah, right. In fact, maybe this is worth just looking at quickly. If we just look in the Symbology tab for a second, you can see the histogram that divides up these colors, and you can move. Like if you wanted fewer tracks to look alarming, you could, move this up a little here, and that would cut down on the number of red. And so then you can use these divisions in your formula, in the index that builds your formula. Okay. So we have the exposure, we have the elderly people, we have the pregnant people, and we add them all together and change the symbology a little bit. And these black tracks are the ones that scored highest on the combination of the 3, where the combination is just a raw sum. So there are maybe 15 black tracks here. As I was showing you with the symbology, if you told me you only had money to fund this intervention in 5 tracks, we could redisplay this. By sliding this slider up until we found, just a few of the worst off tracks. So sort of whatever your resources are, we can find a visualization that shows you where you should direct them. Okay. Now, let's check my work, because my work was not perfect. I decided on the pollution impact by using a dispersion model. Much more common, like what public health people will usually do, is they will have on-the-ground measures of air pollution. In fact, after this fire happened, a private company went around with like a benzene meter and took readings on the ground. I didn't have access to those readings because they belonged to the company and it wasn't easily accessible from the Texas Department of Environmental Quality. Probably could have requested it. But what they do have is standing on the ground monitors. There's a website. Let's see if we can take a quick look at it. So these are all the monitoring sites in Houston. There's a few problems with getting this data. First of all, they don't all monitor the same stuff. And none of them monitor benzene. A number of them measure ozone, and over time, benzene breaks down into ozone. So I decided to just look at the ones that monitor ozone, and I made the sort of arbitrary decision to look on March 21st, which was the day after they made everybody stay indoors. Personally, I don't know how long it takes benzene to turn into ozone, but this seemed like a plausible thing to look for. This was kind of handcrafted artisanal data because there is no one table where you can get all of these at once. You have to click on each one, get the address, get the maximum ozone reading for the day. So I only did about a dozen of them because it took a long time. But Then I geocoded them, and quite a few of them showed up in the center of Houston, like at the zip code centroid. So I had to move them out to their location. So we only have a few of them. But these points are associated with an ozone reading, the maximum daily ozone on March 21st. And we can see them visualized with a symbology that shows, instead of their locations, the magnitude of ozone at that station on that day. So just looking at these, what do you think about my plume?
Pretty good.
It's not too bad. Maybe it should be like a little bit more to the southwest instead of due west. Well, we can find out, because GIS has quite a lot of tools for what's called interpolation. What interpolation does is, if you have point measurements, it will fill in the empty space between the point measurements with a reasonable estimate of what could have been the value there. There's a heck of a lot of algorithms for interpolation. They all come out different. I used sort of the snazziest one, which is called kriging. So I ran the kriging tool, and again, the output I get is a raster. It's a continuous surface made of pixels. And I think it shows that the impact is more to the south-southwest than the plume I initially calculated. Okay. And the other nice thing about the Krieg surface is it actually has the numbers in it are relative to the numbers that were read at the monitors. So for example, this monitor had a maximum value on that day of 75. These pixels here have a value of 70. And as you drift away from that monitor, they go down 68, 67. And then as you get to this monitor, that one had a value of 67. So it's building a continuous surface between these known locations. Okay. So I don't think I did too bad for not knowing where the wind was blowing, but this would be a much more accurate surface to work with. All right, those are the activities that I developed so far in the demo. What I'd like to do now is certainly take questions. And then if we don't have any questions, I guess I could show you how to turn this surface into census tracts, if you were interested. But before we do that, or instead of doing that, let's ask some questions about GIS in general, or the demo that we just did today. Inverse distance, well, I can show you what it looks like. It tends to make these odd little bubbles. In other words, the point location has a lot of effect on the area immediately around it. And that effect drops off considerably at a distance. I'll show you what it looks like. It's easy to run it. So tools. That one lives in Spatial Analyst.
And if I could add, like, if we had sources, if the dots were like sources, then you might think, oh yes, the pollution would drop off in an inverse distance type relationship. But these are monitors, so it's not actual source, so maybe a more even distribution, would be more appropriate here.
And also, kriging takes in like several neighbors into account. But I'm just going to show you what it looks like. It's not terrible. Like, all the results are good. Let's run it on air monitors. And here would be an example of the output you get with the IDW surface. Let me turn off some of this so you can see it a little bit better. And I can even change the symbology so that it matches, so you can compare apples and apples. We can give it a stretched symbology. That means a continuous symbology. and we can change its colors to the sort of color scheme that I've been using. And so that's how the IDW surface looks different. It always comes out kind of speckly like that because each point location really affects its immediate neighborhood. It's not bad, and actually it shows about the same thing, that I should have been aiming a little bit more to the southwest. But that's why I chose Craven. Okay, yeah.
So, I mean, there's this great interface, and I'm wondering if you wanted to open the black box to understand what was going on with the kriging or the inverse distance weighting, can you do that?
You can't see the code that runs these tools. Mm-hmm. However, they have pretty good support materials that link you out to, say, papers that they've used to develop the tools, so you at least get enough for research purposes. And again, you can write things yourself, so if you feel strongly about a way it should be done, you can write your own. Yeah. Mm-hmm.
There's not a dialog box like running in the background for you to see it.
You get feedback from the tool. There is a dialog box that gives you errors and progress, but it doesn't show you the actual script. I mean, it's proprietary, so it doesn't show you the actual script, which is kind of too bad, but that might be a reason to use QGIS. It's free and open source, and you really can see the, yeah.
Is there kind of a standard for how many data points you should have for a geographic area in order to do like a spatial interpolation that's considered valid?
It would depend on the application. So that is entirely a science question. It would be different for air pollution than for, finding minerals. And, I mean, these interpolated surfaces are used for all kinds of things. So you would have to do the actual research in the literature in that topic to know. Yeah, there's no one answer.
In this, could you input not just weather, but like land geography?
Yes, absolutely. You can put like a topographic layer, it's called a DEM, a digital elevation model, and you can use that to complicate this analysis. For example, if there were barriers, I can run these and like cut off the ocean. That's one technique. You can slow things down by having, a mountain range or something. Yeah, that is possible. Or alternatively, if there are channels that things flow in, like if you're doing water pollution, you can limit the flow to those channels. Is your question back there? No. Okay.
I like your contrast of the buffers versus kind of the kriging, because the buffer doesn't.
The buffer is it's so simplistic, and once you get to this kind of interpolation, it really is telling you a lot more. I mean,
the buffers are kind of arbitrary. Again, you could go to
the
I mean, it would really depend on. I mean, it could be improved if you said, okay, I'm interested in particulate matter, and so that might have one kind of buffer, and this gas might have a different relevant buffer.
But it's nice to have directionality and medium, like some sort of understanding of the medium. Yeah. All right. Well, shall I just quickly show you how we could say, if we like this surface, we could turn it into census tracts. Again, all of this is quite straightforward. It's just tools. I'll go get the toolbox.
I would love to hear too. Like, it sounds like there's enough. It's accessible enough that you could really do some damage.
Yes, you absolutely can. Yes.
So it sounds like you fudged something, and you said you've seen some other common mistakes. Are there other common mistakes?
I mean, I could interpolate zip codes. I mean, you can create completely meaningless information with GIS. You do have to be careful. Actually, I say that, but generally zip codes are stored as texts. But I mean, the equivalent of doing something like that, you could absolutely, just create nonsense. And people do. And there's actually one more thing. I only have 5 more minutes with you. This is like the one thing I want you to take away with you when you go out into the world and you see other people's GIS analysis. The visualization is beautiful, but the visualization is art. It's not science. And you can change this to get it to communicate anything you want. Let me show you. And I'm going to do that instead of the the zonal statistics because that's less interesting. But I can display this depending on who I am and what I want to communicate. I can change this stretch. Let's see. To make it look like there's less air pollution. To make it look like there's more. I could give it like a less alarming color scheme. Like what if I showed this pollution in shades of green? And I'll take away some of that contrast. And now maybe it doesn't look like something that you're so concerned about. I can even make classes on this. I can, instead of having a continuous stretch, I can show it in, well, I can make it look like there's no air pollution. But I can show it in bands, sort of just like I divided up the vector colors into bands. Maybe I want to minimize these red bands. Well, I can, move this value. That's just a label, excuse me. I can move this value up so that the orange goes all the way to, 73. And now I hardly see any red at all. So anytime you see a GIS presentation, someone made decisions about this stuff. They made decisions about that formula that I told you, like I just did a simple sum, but they could put weights in there. They made decisions about the variables that went into it and the way the formula was put together. And they made decisions about the visualization. So something that looks wonderfully scientific and objective has the potential to be a bit of a sales pitch. So, yes.
Are there reporting standards if you're creating a GIS map like this that's going into a scientific article? Like how many of these decisions do you need to disclose?
They're not commonly disclosed. If I were doing it, and I wanted to be responsible, I would at least come up with a scheme like quantile that has some meaning behind it. But then again, I have to tell you, if you want to make it look like something's going on in a map, use quantile. Like if there's very little variation and everything is kind of the same, use quantile. It'll suddenly look like there's a lot of activity, even if there's not. So even if I have a defensible scheme like that, it can be trying to show what I wanted to show.
So when you read these papers, is there anything we should look, not just look at the map, read?
Yeah, I would just think a little bit about, it's less a problem in scientific papers because we assume someone like read it and thought about this, but especially like if you're going to a zoning board or if you're going to some hearing from the Texas Environmental Agency and people from the Deer Park facility are presenting, just be a little suspicious. That's all. All right.
How well is this so like if you ran this in ArcGIS and then you ran it in some other program, same data,
Same parameters, same data, it'll come up.
Will it recapitulate the same way? Yeah.
It may not have the exact same symbology, but if I ran the exact same tools, I should be able to point click on a location and get the same value out. Yeah. Mm-hmm.
Well, this was fantastic to see this illustration, and so you've recorded it.
I have recorded it, so I will send you the video. Yep.
Okay. And if you're interested in, gaining these skills, you can take the course. And we also have an excellent GIS library with a lot of workshops and things.
Yes.